All right, lecture 3. I'm pleased to see the audience is not dwindling. Some hardcore individuals waking up early. Okay, so we move today to the specific case of simulating systems that are what we call in the jargon powders. That is collections of crystals with no particular orientation, such as you would have if you grind some solid, or equivalently, for example, flash frozen solutions in biological EPR spectroscopy, essentially systems without a macroscopic order. There is, of course, microscopic order. Every protein or whatever it is folded and in the molecular frame directional, but overall we have every possible orientation of that system in the sample. Surprisingly enough, the basic mathematics of simulating such systems, well, you build the Hamiltonian, you put it together, you exponentiate it, and you propagate your system forward in time, is actually identical to what we had so far, except for one thing. The coefficients in those Hamiltonians now have directional dependence because interactions are anisotropic, shielding, dipole-dipole couplings. Interestingly, even J coupling, although anisotropy tends to be small. And so our mission today is to learn how to rotate spin interactions and spin Hamiltonians in a systematic way so we don't get bogged down in trigonometric nonsense. And then also to calculate integrals over all possible orientations. And that is surprisingly non-trivial, but necessary because the instrument only detects the total magnetization of a disordered sample, and therefore we must sum up over every possible orientation of it. Okay, so let's get going. And I will start from a bird's eye view of the mathematical structure of what we are seeing so far, because this is super important for the subsequent slides. You are all chemists and biologists. You have not been exposed to this in your undergraduate mathematics, but complicated as this looks, it's actually fairly simple. So our philosophy, as it were, begins with a set. And a set is simply just a collection of objects of some kind. Could be numbers, could be functions, could be operators, could be ordered or disordered, doesn't matter. It is a collection of things. And then what we also have that we use a lot is a field, and field is where numbers live. So this is a field in the mathematical sense. And we obtain a field by taking a set and adding addition, multiplication, and the inverse operation. So remember, just scalar numbers, we can add them, we can multiply them, we can invert them. And so the result is called a field. If we put these things together, if we create a set of, for example, vectors or functions or matrices, we allow them to be added and subtracted and multiplied by a scalar. The result is called a linear space. And this is where linear combinations live of, for example, functions or operators. You can add them up with some coefficients. And that is the basic structure of quantum mechanics. For example, the set of all wave functions is mathematically a space because you can add them together with some coefficients. If we also permit those functions to be multiplied and those operators to be multiplied together, if they're matrices, so we add a different kind of multiplication. So previously, this multiplication was by a number. But if we define a multiplication between members of this set, then the resulting object in mathematics is called an algebra. Right? It's slightly richer than a space because you can also multiply its elements together. So the set of all functions, for example, a set of all Gaussians is an algebra because a product of two Gaussians is another Gaussian at their center of gravity. So it is closed under that transformation. Or a set of all matrices can be viewed, excuse me, as an algebra because you can multiply them together and the result is also a matrix. If we define a commutator, the result is called the Lie algebra. It's actually a less general object than the full algebra because this commutator bracket is somewhat less general than the associative product. And this is where our spin operators live. because we've got commutators there. So remember, Lx commutator Ly was ILZ, and our algebra of spin operators was closed under commutation, and therefore it is a Lie algebra. And remember what we did in the very first lecture, we exponentiated the Hamiltonian to obtain the propagator, and mathematicians call the structure where we have the exponentials of all such operators a Lie group. And as you can see, the group of all propagators, for example, if A is the Hamiltonian, is a Lie group. And then there are various other cosmetic things around it. This Lie group is differentiable with respect to, for example, time. So with respect to its parameters, and it's also a differentiable manifold. And these things we will not cover here, but what we need to carry away from this is that we start with a set. We define a few operations and we go up into a space, define a few more operations, go up into an algebra and a Lie algebra, and finally, when we take the exponentials of those matrices, that is a Lie group. This structure will now appear throughout our discussion of the rotation process of the spin Hamiltonian. Okay, so groups in general, what do we call a group? You are chemists, you've done crystallography, you've done basic Huckel theory, you've done symmetry in your life, so you hopefully remember, I mean, if I'm lucky, even character tables, some of you. But in general, a group is a set with an operation that is defined in the following way. For any two elements, so this inverted A means for any G and H belonging to the group, their product is also in the group, and that's called a closure. And then there exists a unique unit element. So this E and an exclamation mark means there exists, and a unique element E, such that for any element of the group, E times G is the same element. So this element does nothing, right? In the case of matrices, it's a unit matrix. In the case of operators, it's an operator that doesn't do anything. So there is a unit element. And finally, for every element of a group, there is a unique inverse. So for any G in G, there exists a unique G minus 1, such that the operator by its inverse is the unit matrix. And you can see that rotations satisfy these properties. A superposition of two rotations is another rotation. There is a unit rotation that simply leaves everything in place. And for every rotation, there is a unique inverse that undoes it. And therefore, this set of rotations in three-dimensional space is a group. Furthermore, because the three angles are the continuous parameters, it is a Lie group. And so every rotation can be expressed as an exponential of some matrix. So let me give you an example for the rotation group in 3 dimensions. This you all, of course, remember. If we want to rotate something in this case, YZ plane, then we multiply the X coordinate by 1, and we mix the Y and the Z coordinate using cosines and sines, and that's your standard rotation matrix from just basic geometry. What is less known and what chemists do not really explain is this Lie group property, is that this matrix is guaranteed to be a complex exponential of something else, and this is called a rotation generator. And that's the angle. And if you do this mathematics, if you take a log of this matrix at the origin, the generator is actually quite simple. You can see here, it only has minus I and a plus I. And if you multiply it by some angle and take the matrix exponential, the result is your rotation matrix. And so this is a tiny little peek into a much larger chunk of mathematics called the theory of Lie groups. And this is Sophus Lie, and fundamental equations of physics, in general equations of motion, conservation laws, you know, fundamental things like Schrödinger's equation, you've seen that argument in the first lecture as well, are consequences of mostly just Lie group theory. Everything we have in physics ultimately boils down to fundamental symmetries of space-time, which are then described by Lie groups. Okay, so let us proceed with the rotations. As I've mentioned already, a superposition of two rotations, so product of two rotation matrices in this case, is another rotation, so we have the closure. Rotation by a zero angle is a unit matrix, and so we have a unit element, and the rotation can be undone, and so there is an inverse, and so it is a continuous group with respect to the rotation angle. Now, there's a wonderful relation in mathematics that allows us to easily find the expression for that. If you take the matrix exponential of a derivative operator, the result is just a finite shift. So if you act by an exponential of a derivative on a function with this parameter alpha, you shift the entire function. And if this parameter is an angle, you would just rotate that function. And so a rotation around a particular axis by an angle alpha is just the exponential of the corresponding derivative. If you go through the trigonometry here and work out the corresponding Cartesian expression, it turns out that this rotation generator is minus I d by d phi. If you work through the polar coordinate system and do it in Cartesians, it turns out this is x d by dy, y d by dx. And those of you who remember angular momentum theory will recognize the LZ angular momentum operator. And so the generators of the rotation group are actually angular momentum operators. And this is the consequence of the fact that reality is isotropic. If you rotate coordinate axis around any physical system, the physics doesn't change. That's a fundamental theorem, and that's in fact a consequence of Emmy-Noether's first theorem. So any continuous symmetry implies a conservation law. So in this case, the continuous symmetry is rotation, and the resulting conservation law is the conservation of angular momentum. So this is the deep link between the angular momenta and rotations. Angular momentum operators are the generators of the rotation group. And then all the usual things that you have seen in the angular momentum theory. These commutation relations to us physicists are just commutation relations, but to mathematicians, they're called structure relations of, between the generators of that group. And then the easiest, the best possible parameterization, so a rotation around the axis n by the angle alpha is the matrix exponential. So that is the x component of the direction and the x generator, y component of the direction and the y generator, and finally the angle. So any rotation can be expressed as an angle and an axis. So the axis is directed somehow, there's a single angle. It's somewhat counterintuitive, but any rotation can be parameterized like that. These things where linear combinations are, remember what I told you at the in the very first slide. As soon as we have linear combinations of operators, and as soon as we permit products between operators, this is called an algebra. And so this is, in mathematical language, the algebra that is generating our group. Right? So these are generators. Once we take the exponential, this is called the exponential map. This is an element of the group, and these are group parameters. So this is your whistle-stop introduction to the theory of continuous groups. And then every group has an associated invariant, or more. In fact, the rotation group only has one. It's called Casimir operator, and this is the sum of squares of all the generators. And this is your usual total momentum, or in the case of spin, the total spin. And it has a special status. It doesn't actually even belong to the Lie group itself. It sits on the outside in the envelope, but it commutes with all group elements, as we all well know in magnetic resonance. It enumerates irreducible representations because it is responsible for the total momentum or the total spin in our system. And it always corresponds to a conserved quantity of any dynamics that obeys the corresponding symmetry. So all of this goes back down to the already mentioned Noether's first theorem. Every continuous symmetry yields a conservation law. When the symmetry is time translation, energy is conserved. When the symmetry is spatial translation, linear momentum is conserved. When the symmetry is rotation, it's the angular momentum is conserved. And when we go to space-time and the Lorentz group, the corresponding invariant is the total momentum, which is the orbital one plus the spin. Okay, so how does this all help us? Remember what we had set out to do. We need to learn to rotate our Hamiltonians in a very systematic way. If you've ever looked at relaxation theory studies of, for example, polyubiquitins, you will remember a rather complex chains of rotations. You would have the NH vector somehow tumbling in the molecular frame, you would have some alpha helix moving relative to the rest of the protein. You would have two ubiquitins moving relative to one another in a linker. And so it's one rotation on top of another, on top of the third, on top of something else. If we attempt to do that trigonometrically, goodness help you, you will instantly get stuck in the kind of trigonometric expressions that not even Mathematica can reasonably process. And so we need to find a systematic way of rotating that. So the one that is historically used, which I don't actually recommend for reasons that we will see in a moment, goes back to Leonhard Euler. He was working in St. Petersburg actually at the time on the invitation from Catherine the Great. And so what he proposed, there are many ways of expressing this, but this is one of the most straightforward ones. You take the object, you rotate it around the z-axis by some angle, you rotate it around the y-axis by some angle, and then again around the z-axis. So it's called the ZYZ convention. And there are two things about it. This is an active rotation, so we rotate the object, not the coordinate system. For physics, this is very appropriate. We are not in aircraft engineering where the rest of the world rotates around you. We have a fixed laboratory table and everything rotates relative to that table. So for the avoidance of confusion, I would recommend that you all always use these active rotations. And then ZYZ is really easy to remember. So if you have the three alpha, beta, gamma Euler angles, well, rotate it around Z by gamma, around Y by beta, and again around Z by alpha, and that's your Euler rotation. This is way easier than these horrendous diagrams that you sometimes see in people's books, which even I could never understand, right? They're like, there is this token picture. Okay, let's get it off our heads. This is the easiest way to describe Euler rotation. But a much better parameterization is this angle axis that I've mentioned. And the reasons for that are mostly mathematical. Firstly, if you need to do a composition of rotations, right? So find out what are the parameters of a single rotation that corresponds, you know, to some sequence of them. In Euler angles, this is a disaster. But in angle axis parameterization, it's actually quite easy. There are simple expressions for composition of rotations in them. Then the second problem, if you look at the way that irreducible representations work, so these are spin operators, for example, of different sizes, and these are corresponding exponentials. The three generators here, the first one is the same as the last one. This doesn't look like a big deal on the surface for Euler angles, but this breaks mathematics in dramatic ways. What this means in practice is this is a slightly irregular parameterization of the rotation groups, the ones that Euler has proposed. And it's possible to go forward from the angles to the rotation, to the matrix that does the rotation, but going backwards is a very insidiously unstable process. Those of you who have ever worked with trying to find Euler angles that correspond to a particular rotation, you must have lost a significant fraction of your hair in the process. Len is smiling in the back. Sit in there because he knows exactly what I'm talking about. He's written a review on the subject. So recovering Euler angles is a disaster, and I would not recommend anyone to do that. Either keep the rotation matrix as there is or use the angle axis parameterization. Anyway, so matrix representations of that stuff are called Wigner-D matrices after Eugen Wigner. And so our mission today is to learn to rotate our interactions into the molecular frame and onwards from there, and then to learn to compute the powder average over all possible orientations. And so since this is a tutorial into the fundamentals, I thought I'd give you this whistle-stop tour of group theory, which you can then explore on your own. It's a vast subject, of course, but unavoidable. If any of you were to go professionally into relaxation theory, into solid state NMR, or God forbid EPR spectroscopy, then you need to know all of this really, really well. Right? So however complicated, this needs to be known. Okay, so let us introduce something you must have heard about if you are participating in this conference and you're a PhD student, that is irreducible spherical tensors. Remember the angular momentum theory. We had these spherical harmonics that were the eigenfunctions of the total momentum and the eigenfunctions of the Z projection. Chemists in general know these things as the atomic orbitals. Remember the s orbital, the p orbital, the d orbital. So these fancy angular shapes that you have, they are actually spherical harmonics. And so they are the shapes of atomic orbitals. And of course, they are there because an atom is spherically symmetric. So we have these functions. They're pretty simple. And what is particularly appealing about them is their rotation properties are very regular. If you want to rotate a spherical harmonic, you just multiply it by the elements of those Wigner matrices that I've shown you in the previous slide here. You can see they're quite easy to compute. MATLAB will just compute them in one line. Here they're just exponentials of matrices. And so this, however horrendous this might initially look, believe it or not, this is the easiest and the most consistent way of rotating things. Initially, it seems complicated, but as you stack rotations one after the other, the complexity does not increase. If you were to do it trigonometrically, you know, 3 rotations in a row would blow out into some terrifying combination of sines and cosines, which you will never simplify. However, if you stack together 3 rotations that are done like this, you just have 3 sets of these numbers, and that's the end of it. Easy to calculate, easy to program, easy to debug, easy to use. More important is the formulation of Redfield theory. Right? The relaxation theory essentially includes both the spherical harmonics and the Wigner functions. And so if you are to understand how Redfield theory works, you would necessarily have to go through them in some detail. That having been said, they're actually quite simple. The Cartesian expressions are here. So y10 is just proportional to z. And 1 plus minus 1 is just x plus minus iy. So they are fairly simple Cartesian polynomials. And these polynomials, as I've explained, by some good luck, just happen to have super regular rotation properties, easy to rotate. And what we want is spin operators that would be easy to rotate. And so constructing them is therefore quite simple. The only thing we do is we replace in these polynomials, we replace x by lx, y by ly, and z by sz. And so we will then have spin operators with exactly the same simple rotation properties. So what we simply do is we replace x, y, z by lx, ly, lz, and the resulting like operator spherical harmonic is called an irreducible spherical tensor. I ignore the word tensor, it's just a fancy word for a matrix in this case. So these TLMs are simply spin operators with exactly the same rotation properties as spherical harmonics, which come out of the rotational symmetry of physical reality and therefore are easy to rotate. Okay, so how do we do it then? All these matrices are tabulated and all of these coefficients are tabulated. They're simple linear combinations of the elements of, for example, the CSA matrix or the dipole matrix. And so our spin Hamiltonian, for example, between spin L and a spin S, contains 3 types of terms. The isotropic terms that do not depend on the orientation, and the anisotropic terms that do. And all our interactions, at least in nuclear magnetic resonance, are either linear or bilinear or quadratic. And so what in principle would have been an infinite series actually terminates at the second rank. In EPR spectroscopy, because zero field splitting is more complicated, you can go to higher ranks. But here we've got this second rank. And these rank 1 terms, they're called antisymmetric terms. They are uncommon. You only see them in the chemical shielding in paramagnetic systems. So if you have a dysprosium next to your nucleus, then these terms will be significant. There's significant antisymmetric shielding components there. But if it's a diamagnetic molecule like a tryptophan or something, you can generally just ignore the antisymmetric components. And your tensor is anisotropic, but as a matrix, it is symmetric. Okay, so what does the software do? Notice I glossed over all the technical details here, and that is intentional, right? So this is when the software comes in. It calculates all of these irreducible spherical tensor operators for you. It calculates all the coefficients for you. The only thing you need to specify are understandable things, like what is the chemical shift, what is the chemical shift anisotropy, what are the Cartesian coordinates of the atoms. It is the job of the software to take those coordinates, to work out the dipole tensor, to expand the dipole tensor in those irreducible spherical tensors, and take all the pain out of this picture. The only thing you need to do is the generic group theoretical reasons for why this is happening that I've just painted for you. Okay, so the software will compute all those operators, will compute all those coefficients, it will make that Hamiltonian, and it will correctly apply these rotation equations to position all of your interactions in the molecular frame, and it will just throw out the Hamiltonian matrix for you. And by now you know what to do with it, right? If you have the Hamiltonian, you exponentiate it, multiply it into the state vector, that's your trajectory, that's the simulation done, right? So compared to 20 or 30 years ago, all the pain of manual transformations of these things has been taken out. So essentially, at each specific orientation, the software will calculate this D matrix, it will correctly multiply it into all those operators, and it will rotate your Hamiltonian. Then, as we described in lecture 1, you run the simulation, and then the interesting question crops up. Well, okay, we run this simulation multiple times at all the orientations of our system. What do we do with it? Or we can just add them all up, or we can average them, or we can average them with some weight. What do we do? Turns out there's a giant number of ways to calculate spherical integrals, because that's what we're doing. We are calculating an integral over all possible orientations. This is an example of a spherical quadrature grid. So these little points are the orientations on the surface of a sphere, and the little polygons are the corresponding area of the Voronoi polygon that is bounding that point. So we could run the simulation multiple times at all of these different orientations, multiply them by these little area elements, and add it all together. Turns out that's one of the worst possible ways of doing that. So many grids have been proposed over the years, literally dozens. This is a Fibonacci grid when the positions, the angular positions of these points are parts of the Fibonacci sequence. You could take an icosahedron and subdivide the faces of an icosahedron to get an icosahedral grid in this case. You could do the same to an octahedron and get a slightly different grid. People have gone into various empirical things, like we just scatter the points on a sphere and we minimize their repulsion energy, assuming they're charges, and they'll spread out on the sphere. And that's called a repulsion grid, or more generally an optimization grid that optimizes some functional. We could take inspiration from the natural world. We can take a look at how scales on a lizard are growing, or how Eskimos are building their igloos because they're hemispherical, and that's an igloo grid. So it is a giant number of methods, or we can use group theory. This is the so-called Lebedev grid, and that is ultimately turns out the only one that is defensible in this case. So let's go into a little bit more detail, right? So now that we roughly understand how to do each individual simulation, let's now think about how we put them together into the powder average. Okay, so again, back to formal mathematics. If a Hamiltonian depends on some spatial parameters, in this case, 3 angles, and on time, it's a fundamental theorem in mathematics that you can expand it in some functions of just the coordinates and some functions of just time. In this case, the coordinates are just alpha, beta, gamma, for example, the Euler angles. You can do the same to the density matrix, and so multiple simulations can be run in the time domain, and then it is possible to find such points in the parameter space. It was Carl Gauss that worked it out, that the integral is exactly equal to a linear combination of the values that are computed at those points times some weights. that you get out of Gauss's procedure, and this is called Gaussian quadrature. And the choice of these functions is with the user. If it's, for example, Legendre polynomials, it's called Gauss-Legendre quadrature. If you choose Laguerre polynomials, it will be Gauss-Laguerre polynomials. If you choose spherical harmonics, it's a spherical Gaussian quadrature. And so what we want them to be is spherical harmonics up to a certain rank. So empirical expressions, we have our function of the angle, that is the full angular integral. So we can approximate it by a linear combination of the values at those points in that grid times, for example, the area of that polygon. But that is very empirical, right? This is our intuition about what a good grid might look like. A decent grid should satisfy this Gaussian condition. Notice the difference, right? This is an approximation. It's the usual finite interval approximation to an integral, right? You remember, you know, the rectangles, the trapezium, the Simpson, and so on, and that's just the extension to multiple dimensions. But what we do want instead is not an approximation. We want the exact thing. And actually, Gaussian quadratures makes it possible if you are bounded on the spherical ranks. Okay, so there are Lebedev grids made by Vyacheslav Lebedev actually not too long ago, maybe 20 or 30 years ago, that take the rotation group. You have seen that the spherical harmonics come out naturally, and so they are the natural basis for this Gaussian quadrature. And so Lebedev has worked out the weights and the point locations that guarantee the exactness for this for some rank bounded, so for L smaller than a certain number. And then if you compare this, so this is the integration error, right? So the low was a beta as a function of the rank of this spherical harmonic. So it goes S orbital, P orbital, D orbital, F orbital, and so on. So the angular dependence becomes sharper and sharper. And this is how the accuracy changes as a function of that spherical rank. You can see all the grids that I've shown you in the previous slides, repulsion, icosahedral, octahedral, igloo, Fibonacci, and maybe 24 other empirical grids. They are not terribly accurate to begin with, and as the rank increases, they get even less accurate. You can see Lebedev's grid blows everything out of the water. It's actually machine precision accurate, right? Up to the rank that is specified here. And then it loses accuracy just like everything else because it's not designed to process those ranks. And there are Lebedev grids of various ranks all the way, I think, to 131 that are tabulated. And I think the situation in the angular integration community can be described like this, right? There's one thing called Lebedev quadrature, and then there's all these hillbilly grids that are not particularly interesting or accurate. So as of maybe 20 or 30 years ago, the problem has been solved. And if you are rank bounded, there's only one quadrature you can defensively use and everything else is nonsense. Right? The trouble, of course, is that in magnetic resonance, we're not very often rank bounded. In electronic structure theory, they are. And so they've got this luxury of machine precision. In our case, sometimes we're not. And if you are here, then of course, every grid is as bad as every other grid. And then it doesn't matter which one you use. And sadly, in magnetic resonance, we're usually here. Okay. So examples, this is a two-spin system with a dipole-dipole coupling in it, just a pulsar wire, solid powder. And if we have 2 points in the spherical, 200 points in the spherical grid, you can see these wibbles and wobbles, right? These are the inaccuracies of our powder integration. If we increase the number of points on that sphere to 1600, it gets a little bit better. If we increase it to 6400, this is your standard strong dipole coupling, and they're bent inwards because you have a minus in the dipole-dipole interaction, right? Remember the roof effect for the J coupling, it's XX plus YY plus ZZ. The dipole-dipole interaction is ZZ minus XX minus YY, and so the roof is inside. But you can see actually that is our big tragedy in spin dynamics simulations, that as soon as it's a powder and you want a reasonable resolution out of it, we need thousands, sometimes hundreds of thousands of independent simulation to get that powder pattern. Thankfully, the calculations are, of course, individually independent from one another. And so the problem is quite easy to parallelize. And so if you have a cluster with a couple of thousand nodes, lovely, right? You can send it there, then collect. And so the scaling of the parallelization in this case is virtually linear. A dramatic example, this is a nitrogen 14 and a mass spectrum of, I think, glycine-alanine dipeptide. You all remember that our nuclear quadrupolar interactions are in the megahertz, but of course the relaxation time in the solids can be quite long, and so the lines are sharp. And in this case, there's no hope with a few hundred points. It's not terribly satisfactory even with 10,000 points. You need 160,000 independent simulations to converge this powder average. There are various other ways in frequency domain, like EPR spectroscopy. You can do adaptive spherical grids in that case, and things become a little bit better, but it is only possible if you have slow passage type detection. So Spinach comes with a large collection of these spherical quadrature grids. I would also encourage you to explore Simpson, which is a package that is narrowly optimized for solid state and mass spectroscopy. You would have a lot of examples there of things like cross polarization and so on. Between them, Simpson and Spinach, I think, cover most of at least non-spinning solid state NMR. Okay, so this was a whistle-stop tour of the mathematics and the computer science involved. And I gave you this hope that you wouldn't actually have to dig too deeply into all of that math. You need to vaguely understand what's going on, which by now, hopefully you do, but everything else will be done by the software. And so Spinach input data structures are quite simple. There's a sys, which is just system specification, like sys.magnet, 0.3 Tesla, that's your standard X-band EPR. Sys.isotopes, you have electron, nitrogen 14, fluorine 19 and 4 protons. Then there's a bus, that's your formalism and basis set, and you can see why it's called SF10 Liouville, right? It's spherical tensor basis set in Liouville space, and yay, you now know what those words actually mean. All right, so no approximations in this case. And you specify interactions literally by specifying eigenvalues and Euler angles or eigenvalues and some other orientation parameters. So in this case, 7 spins. So it's a cell array with 7 vectors in it. And the eigenvalues for the electron, it's a G tensor. So you've got the 3 eigenvalues of the G tensor. Specify the 3 Euler angles. Spinach will work everything out and construct you the Hamiltonians that you want. All the documentation is on the website. And if you want relaxation, you just specify the relaxations here. Then the couplings, again, you usually know the eigenvalues, the chemists will tell you. Give it the 3 eigenvalues and the 3 angles, that's your orientation, or give it just a 3 by 3 matrix if that's what you know. So some kind of amplitude and orientation specification is necessary, and it supports a great variety. And then the housekeeping functions that pre-process everything and build all the Hamiltonians. One is called create, which simply analyzes what you gave it and throws errors if it doesn't like it. It does quite an in-depth parsing of what you gave it. Basis builds the basis set, irreducible spherical tensors, and so on. And finally, an interesting function called assume. And this matters because the program supports a variety of contexts. In, for example, EPR spectroscopy, you want weak and pseudo-secular in the rotating frame, weak, secular, pseudo-secular in the laboratory frame. In NMR, if it's 2 identical spins, you want weak and secular. If it's 2 different spins, you only want the weak. So depending on the frame in which you are working and which spectroscopy you are doing, you need to retain different terms in your spin Hamiltonian. And so what Spinach maintains internally is every element in the Hamiltonian comes with a little tag that says, okay, which terms of this do I need to keep? And to set all of those tags, you need to call this assume function. If you say assume laboratory frame, everything will be kept. If you say assume EPR, it will keep the weak and pseudo-secular components of the hyperfine interactions, for example. If you say assume NMR, these are our usual rotating frame assumptions that we have in NMR spectroscopy, and so on. So all those tags are automatically set, and a kilometer of diagnostics is printed to the console. Then what do you need to provide in order to run that simulation? Well, all the Zeeman interactions, of course. These are your Schildings and G-tensors. You usually get them, I think for NMR spectroscopists, you just shake your nearest chemist until they tell you what they are. You can get them from CASTEP, ORCA, or Gaussian. I would recommend ORCA. Again, it's an electronic structure theory package that is narrowly optimized for magnetic properties. Frank Nese's group has been at it for decades now. And then Spinach builds you these operators, right? That's the magnetic field, that's your chemical shift tensor, that's your electron operators, and that's your nuclear operators. So that's your Zeeman interaction Hamiltonian. You supply the things you chemists understand. The program takes care of all the matrices. That's an example. This is, I think, strychnine. And you can see the chemical shift tensors are quite anisotropic. And so in a solid powder, you will have very non-trivial things, particularly if you look at the aromatic atoms. An important health warning is if you have a CHNO molecule, you will be okay running Gaussian or CASTEP yourselves. Just set these options, you'll be fine. But the moment you have a transition metal in there, if it's an F element or goodness forbid a D element, you need to talk to a specialist. Electronic structure theory of transition metal complexes is horrendously complicated, disastrously complicated. It's, you know, an unsettled matter in quite a few cases still. So if you have a metal in there, talk to a specialist and they will get those parameters out for you. It's not something you can quickly do. Okay, so internuclear and quadrupolar interactions, J couplings and QIs, dipole-dipole couplings are of course worked out from just distances. There's a J coupling and the scalar product of two sets of operators. Nuclear quadrupolar interaction, it's actually electric, but through a twist of mathematics, it becomes a spin-spin coupling once you are sitting in a nuclear ground state. Dipole-dipole interaction is just a function of the locations. And so the job of good software is to make sure that you are never exposed to all of this mathematical spaghetti that you are looking at in this slide. It works it out for you. The only thing you get in the end is the Hamiltonian matrix that you know what to do with. If you are doing DNP, you will need to worry about this. So all the inter-electron interactions and zero field splitting. Do not use DFT for these things. DFT doesn't even get the sign correctly for zero field splitting. In a few cases, you are stuck with post-Hartree fork like multi-configurational self-consistent field and sometimes even CAS-SCF. So again, electronic structure theory of exchange coupling and zero field splitting is ongoing research. If you need those things, talk to an expert as they will set you straight on that. Okay, so electrons also have J coupling. It's called exchange interaction. They have their own like quadrupolar-like interaction. It's called zero field splitting and the usual dipole-dipole term at some distance. Then electron-nuclear interactions, just hyperfine coupling. Fermi contact is isotropic, and the anisotropic part is just a dipole-dipole interaction. Those are very anisotropic, as anisotropic as they get, particularly in aromatic systems. You can see needle-like tensors. So you need a very large grid to get them correctly integrated. And then, of course, microwave and radio frequency terms, just a cosine times the corresponding spin operators. Note that if you're doing magic angle spinning, that the direction of the radio frequency magnetic field is parallel to the spinor axis. If you're just doing straightforward solid state NMR, it doesn't matter. But if you do quadrupolar overtone spectroscopy, then even the spinning direction matters. So for nuclear overtone NMR, if you spin clockwise, you get one spectrum, and if you spin counterclockwise, you get a different one. And that cost me about a month because I thought it was a bug in Spinach. And then Yusuke Nishiyama told me it's actually true. So Bruker spins in the opposite direction from Baryon. And so you get two different spectra out of two otherwise identical pieces of electronics. Okay, and then kernel functions. So the Hamiltonian will give you the Hamiltonian, relaxation will give you the relaxation superoperator, equilibrium will get you the thermal equilibrium density matrix. If you want to build your own operator, you can request it from the program. You want your own state and Liouville space, it will give it to you. Various average Hamiltonian series and so on. And then, of course, time evolution infrastructure is all in there. So there are pre-programmed pulse sequences, but there are also infrastructure functions that you can use to create your own pulse sequence. It's not any harder than programming a pulse sequence on an actual instrument. You know, look at the examples, modify the examples as you like, and you'll be fine. Okay, and then there's an example. So spin system equals assume NMR. That sets the assumptions. Liouvillean equals Hamiltonian plus the relaxation superoperator. Everything will be automatically computed and a matrix will be returned. Initial state, rho is the state of the spin system, LZ on the protons. Detection state, state of the spin system, L plus on the protons. Pulse operator, L plus is an operator of the spin system, L plus on the protons. Likewise for the L minus, and then Lx is L plus plus L minus over 2. Pulse, rho is the step of the spin system under Lx from this initial condition angles pi by 2. Coherence selection, of course, in a simulation, we have direct access to the density matrix. We can just zero out the coherences we don't like. And so rho is coherence of the spin system, 1H, single quantum coherence, and it will do that. Run the evolution, answer is the evolution of the spin system under this Liouvillean to be detected on that coil state from that initial condition. That's the time step duration, that's the number of steps, returns the corresponding observables. So it's like programming a variant machine, right? Not too different, and of course easier because MATLAB is narrowly optimized for scientific computing. You can see matrices are just elementary variables in here, and vectors, you just do that. Most functions will automatically use the GPU. If you have a nice NVIDIA GPU that can speed things up, the bigger the system, the bigger the speed up, so the scaling is present, of course. Then there are various convenience things. So for example, the powder average that I've just described is actually outsourced to the kernel. You don't need to worry about it. They're so-called context functions. In this case, it's a single axis rotation. So free induction decay here is single axis rotation context of the spin system. Cross-polarization is a pre-programmed CP experiment. You specify a bunch of parameters that the manual will tell you what they are under assumptions NMR. So that's your answer. That's the context. That's the spin system data that you gave to Spinach. Pulse sequence file name, parameters data structure, like what's the spinning rate, what's the spinning axis, what are the radio frequency powers, what's the detection state, and here's the time grid. All right, so you've got 100 grid points and on a full sphere, time step, number of steps, and other such things, and that's the NMR assumption set. So in essence, you look at the manual pages and it's all there, and the program takes care of everything, including the powder average. You simply specify which grid, and you simply increase the size of that grid until the answer stops changing. So that's an example of that dipole-dipole spectrum that I've already shown you. Cis dot magnet, 14 Tesla. Cis isotopes, 2 protons. Inter-Zeeman scalar, these are the chemical shifts in ppm, 5 and -2. So there's your -2 and there's your 5. Intercoordinates, these are Cartesian coordinates. Spinach will work out the dipole-dipole tensors from there, and whatever else you need to specify in there. And then, okay, parameters.spins, the experiment needs to run on protons, beginning in L+, so after the 90 degrees pulse. Detected on the L+, do not decouple. Apply a kilohertz offset, use the spherical grid with 6400 points, sweep width 12 kilohertz, number of points 1 to 8, 0 field 2512 before Fourier transform. The axis is in ppm. Please invert, do not output anything that is not absolutely necessary. And finally, FID is a powder simulation of the spin system under the pulse sequence that's called acquire with these parameters under NMR circularity assumption. And that's your solid state simulation in Spinach. As soon as you vaguely understand where all of these options are coming from, and hopefully you do by now, The rest is fine. Automatic parallelization over the elements of that grid, over as many cores as it finds on your system or your cluster, if you're running MATLAB on a cluster. Okay, so summary. Actually, for static solids, the time domain simulation problem in magnetic resonance is exactly the same as it is in liquids. Exponentiate the Hamiltonian, multiply it repeatedly into the density matrix, and you're done. That's your trajectory. But a logistical problem is we need to do these rotations and these power averages. And as you can see, group theory is quite essential in there. Those of you who are students and postdocs, if you didn't understand a word of what I said about group theory, that's normal. I didn't either. I don't remember who it was. It was Shimon Vegas that was teaching these things to me 20 years ago. And I remember walking out utterly bewildered. So it'll get there, don't worry. So it is essential, and you'll sooner or later pick it up. So simulations must be integrated over orientations, and that, as you saw, is non-trivial. Interaction anisotropies either come from electronic structure theory, or you just fit your experimental data with respect to those anisotropies. And I would encourage you to take a look in particular at Simpson, spinach, and spin evolution. These are the three major packages that will make your life easier for the spin dynamics simulations of static solids. And the spinning powders are the subject of the next lecture. And there things, I'm afraid, are getting even more complicated. Okay, that's me.
Thank you very much for the excellent talk. I understand about the Eskimo, how to build the yeah, cake. But any questions? Yeah.
The quadrupolar NMR, the sensor spinning matter, whether it's anti-clockwise or...
If you detect the fundamental transition, so across just one pair of levels, then it doesn't. So a normal quadrupolar spectroscopy, even under magic angle spinning, the result will not depend on the sense of the rotation. However, in the overtone spectroscopy, it will. I must admit, this is reproduced by simulations, but I think there's only one person in the world who understands exactly why. Two people. One is Lucio Friedman and the other is Yusuke Nishiyama. So even though I can simulate it, I still don't understand why exactly that happens.
But it is true for any second rank tensor interaction, right? Even for CSA, it depends on sense of spinning, unless you have a powder average or unsynchronized magic angle spinning.
This is a difficult question. I suspect you are right fundamentally in that there will be dynamics in some obscure multiple quantum coherences that will always depend on the sense of the rotation. It's just when you only detect a single quantum coherence, then that probably doesn't.
Just I want to refer to John Wa's paper with Marik, Marik.
Mm-hmm.
There, if you take a single crystal, if you do...
Oh, for single crystal, you are certainly right. I mean,
right.
It's obvious for single
You need
crystal.
the symmetry for the spinning sense dependence.
Yeah.
That does,
I mean, in a single crystal, it's a completely different trajectory if you spin it in the opposite direction.
But if you don't do synchronized MAS, it won't show up.
Well, let's stick to static solids for now. Yeah. So.
Okay, thank you.
I have another question. So very insightful talk, like always. Maybe I have a maybe stupid question. So what about using Monte Carlo simulations to?
So doing powder averages by Monte Carlo is the worst possible way to do powder averages. It will converge like a dying horse, really slowly. You will need hundreds of thousands of points. So I think the quick advice is always use a Lebedev grid.
What's the reason for Monte Carlo to be so slow?
Well, it's the same problem, right? So, of course, Monte Carlo is good if you want a very, very high dimensional integral because its efficiency increases with the dimensionality of the space. But in low dimensional spaces like 1, 2, or 3, like we have in this case, Gaussian quadratures are the way to go, right? You see, in some cases, electronic structure theory people, they want that integral to 16 decimal places. And you can imagine how many Monte Carlo points you need to take before your answer converges to 16 decimal places. It's just unrealistic, right? It's of the order of 10 to the 16 squared that you would need to take.
Thanks. You may have mentioned this in the first lecture, but I wasn't here, so I would just point out, because I'm a big admirer of hers, that Noether is Emmy Noether, brilliant female mathematician who died unfortunately young. But my question really is, when we take into account relaxation during the rotations, do you still have a Lie algebra?
No. So the process is modified at the level of the definition of a group. So remember the conditions that we had at the very beginning, that in order to be a group, you must always have the inverse element. However, when relaxation is present, it is a dissipative process. It loses information. You can construct relaxation superoperators that would, for example, zero out the population of a particular coherence, in which case that transformation is non-invertible. And so you are losing the inverse element property from the definition of a group. It is still a reasonably well-studied entity. It is called a semi-group. It does have an algebra, but it is no longer an algebra that is closed under the commutation operation. So various properties like start falling off. The directions on that algebra are called Lie wedges. They're no longer just structured. So essentially, group theory of dissipative dynamics becomes considerably more complicated because of the lack of that inversion property.
Okay.
I have a simple question regarding your frequency domain simulation, time domain simulation. Maybe your default here would be frequency domain simulation, right?
In fact, this is done in EPR spectroscopy. So, of course, many EPR machines, even now, are doing field sweep. So they are not changing the frequency or pulsing, they are changing the amplitude of the B1, B0. And so in that case, it's effectively either a frequency by frequency or a field by field detection. That is something very different, right? So in that case, incredibly efficient powder averaging methods are available. So there's one due to Stefan Stoll, the author of Easy Spin, where the powder averages for field swept EPR simulations are computed with extraordinary efficiency on adaptive spherical grids. Unfortunately, the same methods are not applicable to time domain simulations because you need to know the eigenvalues of your evolution generator in order to apply that method. So yes, you are right, for swept spectra rather than pulse acquire spectra, a different class of very efficient methods is applicable. It's just we never have those situations in nuclear magnetic resonance, unfortunately.
Okay.
Okay. Any other questions? So if not, since it's 8 a.m., and better to close now. And tomorrow we will study a magic angle spinning part of the simulation. Thank you very much.